Hey, chemistry, how you doing? You ready for another flipped lecture? I know I am. Let's jump right into it, okay, shall we? We're looking at ions and isotopes and what those words are and what those atom types are. In a normal atom, the number of protons equals the number of electrons. And so a proton is positive, an electron is negative. When you find an atom out there in its elemental state, it's not bound to anything, then it has the same number of protons and electrons. And the protons are positive, the electrons are negative, and so they cancel each other out with regard to charge, and you wind up having a neutral atom. Okay. Also, protons have mass and electrons do not. So as the number of electrons changes, the mass doesn't change. Neutrons in the nucleus do have mass, and so to get the mass of something, it's the number of protons and the number of neutrons added together. So if we start to mess around with the number of nucleoids, the number of things in the nucleus, then we're going to start altering the mass, right? So that's what today's lecture is looking at. What happens when you alter this balance? What happens when you change these numbers? Okay. Here is, again, just as a review, this is a normal carbon atom. It has 6 protons and 6 neutrons in the nucleus, and so it has an atomic mass of 12. 6 plus 6. It also has 6 electrons orbiting it, and 6 protons in the middle means that a plus 6 and then a minus 6 is a 0 net charge. So this is neutral, and it weighs 12 atomic mass units. Okay, but if these ratios change, then we start to change what we call these atoms, and they start to behave differently, right? If the number of electrons does not equal the number of protons, then there is a charge on the atom, and it's called an ion. An ion is an atom where the number of protons is not balanced by the number of electrons, okay? So one example would be 6 protons and 10 electrons. If you had 6 protons, you have a positive 6 charge. If you have 10 electrons, you have a negative 10 charge. 6 plus a negative 10 is negative 4. So that example, that carbon atom would have a charge of negative 4, and it would be an ion. Anytime something is not balanced as far as its charges go, we call it an ion. Okay, here's a picture of that. Still 6 protons, but now we have 10 electrons. So 10 electrons plus 6 protons is a negative 4 net charge. This is a negative 4 ion. And you'll get to the terminology with anion and cation a little bit later, but this would be an anion because it has a negative charge. Negative ions are called anions. Okay, charges or ions can be either positive or negative, depending on whether there's an abundance or a scarcity of electrons. The number of protons won't change. It's the number of electrons that are changing, right? And an ion can only be formed by filling or emptying the outermost shell, which is called a valence electron shell. You've seen that term a couple times already, but this is the chapter where your book introduces it to you. So a valence shell is the outermost shell of electrons around an atom. And it's only those electrons that can be gained or lost. So a carbon atom could get rid of the 4 valence electrons that it has, but the 1s electrons that are orbiting nearest the nucleus, it can't dump those. So it could become a plus 4 charge, but not a plus 6 charge, right? And similarly, that carbon atom could gain 4 more electrons and fill up the 2p, and it could be full in that regard, but it can't fill up the 3s, right? It can't go to the next level, so it could never become a negative 10 charge or something like that. Okay, so it's only the valence electrons. And then when you look at s and p orbitals, the number of, or the column that it's in helps you predict the charge, right? And so remember that the columns here represent electron configurations. So this is 1s1, this is 1s2, this is 2s1, 2s2, 2p1, etc. Okay? And as you go across the table, you can see that the s's only end, these columns only end in an s, which means their outermost valence shell only has 2. They can ditch those 2, and they could become a positive 2 or a positive 1, depending on which of these columns that they're in. Similarly, these guys over here, they have 7 in their outermost p level. The p level can hold, I'm sorry, they have 5 in their outermost p level. The p level can hold 6, so they could gain 1 more. And they could become a -1 charge, but they couldn't become a -2, -3 because would be full if they had 1 more. So things in this column become a -1 ion, -2 ion, -3 ion, +1 ions, +2 ions, +3 ions. And this column can go either way, +4 or -4. These ones are very hard to get to ionize because they'd have to dump or pick up 4 electrons, which is a huge amount of electrons to change. So generally, the ones that you see here, the +3 to -3 column, don't like to ionize very much. They can ionize. You can make it happen, but they'd much rather form covalent bonds, which we'll get to later. So back to the concept of an ion is what happens when you change the number of electrons. When you change the number of neutrons, something else happens. And we call something with a different number of neutrons an isotope. Isotopes are atoms where there's still the same number of protons, but now we've changed the number of neutrons. So its chemical properties don't change very much, but it weighs something different. It is more massive or less massive, because remember, mass is determined by the number of nucleons, protons and neutrons in the nucleus. And so when we have an isotope, it's still carbon, or it's still hydrogen, or it's still nitrogen, or it's still whatever, but it is more or less massive. And that changes usually not the chemical properties. Usually if it changes something at all, it's going to be radioactive. Some isotopes are radioactive where the normal version of the element is stable. And so we have an example here. If there are 6 protons, and in carbon, in normal carbon, there's 6 neutrons. But here, if there's 8 neutrons, now 6 plus 6 would have been 12. 6 plus 8 is 14. This is called carbon-14. And you are familiar with that term if you've at all been involved in, dating fossils, that whole debate, can you tell how old fossil is? This carbon-14 is one of the principal things that they use to date it because it's radioactive, and we know how long it takes to fall apart, and we can guess at how much C14 there was in the organism at the time that it died, and so they can guess as to how old the thing is when you find it. And we'll get into how that works later on in the year. But carbon-14 is called carbon-14 because it has a mass of 14. Okay, so this is carbon-12, and that's normal carbon. This is carbon's slightly fatter version of itself, carbon-13, and this is carbon-14, very rare, and weighs more because it has an additional neutron. See, this is 6 neutrons, 7 neutrons, 8 neutrons. Okay. Now, when you look at a table and you look at how heavy something is, the numbers are not written as whole numbers. So an original isotope is carbon-12, carbon-13, carbon-14. Example here, right? It's the mass of that particular isotope of an element. But when you look at the periodic table, it's not a whole number. It's a decimal. And that's because they take all of the possible isotopes and they average them out based on how common those isotopes are in nature. So almost all carbon that you find in the world is carbon-12. There is some carbon-13, and there's a very small amount of carbon-14. And so because there is a little bit of 13 and a little bit of 14, we have to average that in, and that's why if you look at the periodic table, the weight of carbon is 12.01, right? Because it says almost all the carbon is 12, but there is some heavier versions of carbon out there. So they take all of the possible isotopes and they multiply them by their prevalence, their commonness out there in nature, and then they average that together. So let me show you how that works. If you have 99.99% of carbon that is carbon-12, then you would have 99.99% times 12, right? And then you would have 0.0006% that is 13. And then you would have 0.0004% that is 14. And then you'd multiply those together and add it up, and you'd get 12.01. I don't know if those numbers work. I just pulled it out of my head. But you see the idea. It's the prevalence of the sample and its weight. You multiply those together, and then you add it up, and you get the atomic weight that represents the average weight of all the atoms of that element out there in the universe. Here's an example of how to do that for magnesium. Okay, magnesium is element number 12, and its atomic mass is 24.31. And that's because most of the magnesium that we find in the universe has 12 protons and 12 neutrons. So its atomic mass is 24. But there's some magnesium, that's magnesium 25, and there is some magnesium that's magnesium 26. 78.99%, 10%, and 11%. Now, when you look at this, you're going to say 78 times 23 is not 18. This little slide is not quite as clear as I would have liked. This is a percent, right? So you'd actually be multiplying by 0.7899 times this to get this. Does that make sense? Okay. So 0.1 times this, 0.1101 times this, and you get these numbers, and then you add these numbers up, and you get 24.305, etc. And you only have significant digits that go, I don't know why they only, yeah, there you go, 4 significant digits on these abundances. And so 4 significant digits in your answer, 24.31. Okay, so that's how that works. You'll do some of this in a lab, and we will make sense of it as we go. If you have any questions, let me know. Put them in the comments field below, and I will try to get to them as quickly as I can, or I will see you in class tomorrow. Jesus loves you, and so do I. See you then.